Hey Louie, I'm just recording this video to show you how most of these programs work because I haven't gotten around to um, basically sifting through all of them and correcting them and documenting them in a form that would be useful without clear instructions on how to use them, right? Especially because a lot of them require these apps here. For example, like I have an app for the Nichols plot, like I have an app for Bodhi plot, and these are just copies of the stock apps that come in the calculator, but I just have separated them just in case I want to have like a Bodhi plot or something here and not interfere with what's already in the function plot, right? So what I will give you is a copy of the backup from my calculator, and you can just go to the connectivity kit and restore that backup. I'll just do this right now. I think the screen recorder is only recording the calculator, but I'll do it anyway. You can just go to the ConKit and restore from this zip file that I'll send you, and it'll do like this. We just clear the memory of the calculator, right? And then you'll have all of the apps here and all of the programs as well, which is like a bunch of programs. Most of them are cast functions. So if you got cast functions, you can't just use them right out of the bat. This is why I preferred sending the backup instead of the file with all of the functions, because first you can copy all of the functions directly from the backup, but if you want to run them on your calculator, you have to put them manually there and then one by one check them to compile them, because otherwise they won't be compiled and you won't be able to use them unless you go through them one by one and click the check thingy, right? Because then they will be stored in the program variables here. They're all here, right? Because cast programs are stored as variables. Anyway, there are some non-cast functions. For example, this keys program, which I'll show you in a minute. This keys program is a user key that brings up a menu of all of my programs. Then I made it just for ease of use, right? And that is related to the EEX user key, right? So if you see, if you take a look here, I don't normally use the EEX key, so I just permanently enabled the user keyboard, and whenever I type the EEX key, it will bring up my functions menu, which has a commands history here of all the commands we have used previously, and several different little categories here. For example, like I have some programs for robotics, just have like homogeneous transformations and Dennevit-Hartenberg transitions and stuff. But let's just focus in these control state space and S domain uh, categories within here. Right, there's some like advanced matrix stuff here, like Lyapunov equations, but I don't know if you want to use that. You're more than welcome to check that out if you want. But let's just do something simple here. So let's start with control S domain here. What we have is the coefficient to transfer function and transfer function to coefficient functions. These work just like MATLAB. If you want like a transfer function 1 over S, it will just give you a vector of the coefficients, because some of these functions here have the coefficients as an argument, and some of them have just the transfer function as an argument, and that hasn't been standardized, which is again one of the reasons that I haven't posted just all of these programs on the forum. Right, so let's just use this second order response here, which just builds you second order transfer functions based on the dampening coefficient and the natural frequency. Let's just say we have a dampening coefficient of 0.7 and a natural frequency of 10 radians per second, and we'll just plot this right away, which is the time response of the system with the transitory response and the steady state gain here, which is should be exactly 1, which comes from this term here, right? So this will give you the second order transfer function. This second order transfer function, we can do several things with it. We can go to the control state space section and say, like, put that in state space form, and we'll just do it. We can do it in the observable canonical form. We can also do it in the controllable canonical form as well, right? And I don't know if you want to go into the state space stuff, but I'll do it anyway. But I'll do it at the end of the video. So first, what I want to do is, for example, like plot a Bode plot of this. I can just go to the Control S domain and Bode plot, and input the function into the answer there, and it will just calculate it and give you the gain in dB and the phase in degrees, right? So you can see here, just keep in mind that the x-axis is not in radians. The x-axis is also in logarithmic format. So this 2 will actually be 10 to the 2, right? So if we want to check the poles, like, we can check the poles of this function here. Let's say, for example, that I want the zeros of the denominator of this transfer function here with respect to the Laplace variable, which are the poles, right? Our poles are these. They are complex conjugated poles at -7, right? And they have a natural frequency of 10 radians per second, which is just the sum, like the square of the root of the sum of the squares of these, right? Anyway, doesn't matter. We can see that like the -3 dB frequency should be close to 10 radians in this plot here, right? And the 10 radians would be 10 to the 1, so it would be aligned exactly with this this line here. If we do like a zoom here and go up to here, we can see that when x equals 1, we have roughly -3 dBs here. So this is pretty much saying that, sorry, the 3 dB crossover frequency is equivalent to the complex conjugated poles. And this should also be 45 degrees. No, sorry, 90 degrees. 45 would be if it's a single pole. 90 degrees, it's both poles, right? Anyway, from this we can calculate like phase and gain margins and stuff. This is boring because it's a dampening coefficient of 0.7, but if we want to do like a dampening coefficient of 0.2, which is a more oscillating response here, we're going to see that there's going to be a frequency in which it has a high gain, right? So if we instead plot the Bode plot of this transfer function instead, we are going to see, sorry, the Bode plot, we're going to see a little peak here. And this peak is essentially, sorry, and this peak is essentially the resonant frequency. The good thing about having all of these graphs here in the function app is that if I want to find out the resonant frequency from the graph, I can just go to function and extremum here, sorry, and you can just go to function and extremum there, perfect, and it will tell me that we have a gain of 8 dB, 8.13 dB at the frequency of 0.98, 10 to the 0.98, right? So I can just shift copy here and get the X position and go to here and just say like 10 to that number, And then we know that at a frequency of 9.59 more or less radians per second, we're gonna have this resonant frequency with a gain of 8 dB. If we want to know the amplitude of this gain, we just take this value, divide it by 20, and take 10 to that power, which will give you the amplitude value instead of the gain in dB, but that's just basic stuff. From this, we can also know the phase and gain margins, but if you want to just get them from the transfer function, there's also this command called gain and phase margin, which just give them right to you. It has a phase margin of 180 degrees and an infinite gain margin, right? We can also have the more robust measurement of a disk margin. Where is the disk margin? Here, which uses the H infinity norm of the sensitivity function. So here we can see that it has an alpha of 0.5 and a gain margin between 0.5 and 1.7 and a phase margin of 30 plus or minus 30 degrees, right? So this is like if we can attest that the controller, the system won't have variations exceeding these, then the negative feedback control system is robustly stable for these parameters here. Anyway, I digress. Also, we can have, you saw that in the function app, like we have the time response of this, and this time response is calculated with the inverse Laplace function here in the HP prime. And the inverse Laplace function has some limitations, especially if we have a lot of poles and a lot of zeros in this. It won't be able to get an analytic expression to solve the differential equations. So let's just add a bunch of poles here. All right, let's add a bunch of poles. And to do the time response of this, we can just go to the EX S domain, TF to CoF. It would give us the coefficients of the numerator and the denominator, and we'll go to the, what is it, step response, which will get like the numerator and the denominator, and a step with amplitude 1. And I don't know if it has, let's just auto scale, and apparently for that it can still do it, right? It can still do it for these. Okay, so let's just say we have a system with input derivatives as well. Let's say S plus 10 on the numerator. Let's see what that does. I don't know if it can do that. Let's just go here, CoF to TF, right? And step response. And it can still do it apparently. Wow, okay. I don't know. Maybe they have changed it in the update, but I remember the inverse Laplace command did not work for a lot of the transfer functions that I use here, especially if they were complicated. So let's just assume that this transfer function is too complex to be simulated in a normal fashion. So we want to put it in the state space format, right? Well, we can do that very easily. We can do that very easily with the transfer function to state space command. It will just give us the system here, which is a fairly high order system, right? Because it has like 1, 2, 3, 4, 5 poles and 1 0, so it's going to be a 5 by 5 A matrix. And if we want to simulate that, we just go here to the control state space and do state space simulation. And it has by an input argument the vector of all of the matrices, then a time step, and then the number of seconds that you want for the simulation. And it's symbol SSF1, which means that we use whatever is in the F1 function as an input. So I'll just give 1, so it gives a step input to the system, right? I'll go back here, and then we will just do an enter. And it did not work, which is weird. Sometimes this happens, and I think it might be related to, again, the compiling of the program. So if anything like this ever happens, we can just go to the program here and search for, let me just put this on the alphabetical order, find the program, symbol SSF1, and just check it again to see if it's compiled. Alright, now let's just do it again. Take this as an input. Okay, perfect. Now it asks us to input the initial conditions. I'll just put them all as zeros, and then it simulates 5 seconds here. It simulates 5 seconds. In red we have the response, and in blue we have the step. Just keep in mind that there is a maximum of 10,000 iterations here. So let's just increase this to what, 20 seconds, right? Oh, okay, perfect. Now we can see that it just goes and stabilizes at this value here, right? And this is interesting because we can use this simulation to simulate like state feedback controllers. It just can't do multiple inputs, multiple outputs, because I haven't programmed that in yet. And we can also use the fit function here to overlay a function from the functions app on top of this line. So you can see that here we have this blue line on top of that, on top of the red one, which is the analytic solution to that equation, right? Oh, okay. I forgot something very important here. What if we want to take this equation, what if we want to take this transfer function and look at all the poles? Well, I have implemented also the RLocus function, right? This will give us the RLocus diagram with a gain step of 1 and a maximum gain of 100. If we do the center here and click plot, it will give us all of this craziness here. And if we want a finer resolution, like I would probably want to find a resolution here. So I'm just gonna put the 0.1 here and lower the gain maybe. Let's just do it like that. That's fine. It might take a little while longer to calculate all of the values because it has to solve a lot of equations. Keep in mind that this might be slower in the physical prime, and it's definitely faster in this like computer version of it. Okay, so as we can see here, we have all of these poles, the 1, 2, 3, and then the conjugated ones. And this one will go to the 0, and these ones will cross to the negative gain. We can go in there and see what the crossover gain is. And here these complex poles will just go over there. And that's all right. Right, we can like program, we can design a PID controller or like feedback compensators for this. But because the number of poles is so high, a better solution for controlling this system would be like a state feedback compensator, right? And then let's just see, let's just say that we want like these poles to be in specific positions, and then we can calculate the eigenvalues and use the place function in the state space to do that, right? But I don't know if I'll show you that here, because I don't know if you're studying that subject. But what the hell, let's just do it. let's just say that we want these poles to stay where they are, and we want these poles to be somewhere else, right? Let's just say we want them to be, let's just say we want them to be, let me turn off the trace. We want them to be here, right? Here and here, which is -5 and -5. -5 and -5. And these ones, let's just say we want them to go to the -10 and -5, right? And the 0 will just stay here. Maybe we can put a pole on top of it. So yeah, okay, let's just create that vector of eigenvalues. Or let's say poles, right? So the poles that we want are -5, -5 times I, and then -5, -5 plus I, and then -10 -5 times I, and -10 plus 5 times I. And we have 1, 2, 3, 4. 1, 2, 3, 4, 5. We need another pole, and we'll just put that pole in the same place of the 0, which is at -10. Or actually, this doesn't make a lot of sense from a control system's perspective. We should probably want 2 dominant poles and put all of those ones way back over there. So let's just see. Let's just do it like this, and then we'll just verify if the A matrix has these parameters later. So, okay, alright. These are the desired poles, and these are the poles that we have. Right, so firstly, we'll just copy this transfer function here and get the state space realization of it using this function. And then we'll just use this set ABCD to set automatically all of the A, B, C, and D variables to these matrices so that we can more easily work with them. For example, like the A matrix is here, right? And we can do the state feedback compensator very easily using the place command. We can just, sorry, that's not it. That's not it either. Pole placement. Okay, it will get the A matrix, the B matrix, and the eigenvalues. And the eigenvalues that we desire are exactly these ones. And then we do an enter. And unfortunately, we have imaginary gains here. Can we have that? That's weird. I've never seen that before. Anyway, let's just roll with it. Oh, okay, I see what I did. I just typed this all wrong. Right? -5 plus I, that's just, okay. It's just plus 5 times I. -5, -5, -5 plus 5. Okay, sorry. That all of those complex gains just came out of this because I just mistyped this pole here. That's fine. Okay, so this gives us a full state feedback gain matrix of this, and this command just uses the Ackermann formula, so it will work for multiple input and multiple output systems as well. So what we can do is just rewrite the system with this gain matrix on it. Right, we can just, let's just do a plus and minus here. Oh, sorry. Do a plus and minus here just to put it in the matrix instead of a vector, and let's store it in the k variable, right? So we know that the K is this thing. And to apply the state feedback to the system, we just create a new state space model, which is A minus B times K, right? And then B, and then C, and then D. And that's our new that's our new system, right? We just go back here and set the A, B, C, and D matrices to that. Anyway, perfect. And now we can just go to the matrix functions here and check the eigenvalues of the A matrix, and they should match all of our desired ones, which is minus 10, minus 10 minus 5, minus 10 plus 5, minus 5 minus 5, and minus 5 plus 5. Also, we can simulate that response. Just go to the control state space simulation. Let's just put like 20 seconds again, and give all of this as an input to that. And wow, it has a very low gain. Interesting. Of course, I mean, it has a pretty nice response here. And it's related to all of those poles, but we just didn't calculate the input gain of the system. So, I mean, why don't we do that? We can do that just by using the expression here. But I mean, a more interesting way to do that is just convert this back to the transfer function and just get the gain from that. So why don't we do that, right? We can go to the state space domain and say state space to transfer function, and input this state space vector to that, and will give us this transfer function here. And then we just get it from the matrix, and use the final value theorem, which is just the limit as s tends to 0 of the transfer function, which will be the steady state gain, which is 2 over 125. 2 over 125, right? We just invert that, and it's 62.5, the gain that we should have in the input of the system. So let's just go back to here. Let's just go back to here. And we have already done this, so we don't need to do it again. Let's just do B times 62.5. And then when we simulate this, we should probably have a unitary gain on the output. Let's just do that. 20 seconds. And here we go. That was it. That's pretty nice, isn't it? Let's just set the scale here. Check it out. All right. This is our response. Directly simulated from the state space system. If we had some specifications, we could use the fit here to lay the line on top of it. This is just that random function, right? This is then the other response. See what we did by allocating those poles there. But we could also plot the transfer function of the specifications and see how it compares anyway. So I think like being able to do that is pretty nice. It will just plot it in this copy of the two variable statistics, so that like you can keep a copy of it somewhere else and it won't interfere with the statistics2var app itself. But anyway, this is very useful to like verify if your controller is working correctly with a simulation instead of just calculating the eigenvalues from this. What else can I see here? We have all of the discrete state space stuff. Like we can translate the transfer functions to Z transforms or to discrete state space representations of it. Like it's not, I don't know if you were studying that. It's not that complicated. But there are just too many things to go into, like the advanced matrix functions here. We have like Kronecker product and Lyapunov equations or whatever. Like if you want to do like a state feedback compensator, we can use like the linear quadratic regulator. We can also do like a Kalman filter with the linear quadratic estimator and do like a Gaussian regulator of it. We have controllability and observability matrices, controllability transformation matrices, a similarity transformation application here. We can calculate all of the Gramians and also the H infinity norm here. Right. So I just suggest that you just play around and just take a look at these. Take a look at the programs, right? Like I said, I haven't gone around to rewriting a bunch of them because they all depend on each other. For example, this let's see, Lyapunov. This Lyapunov solver here uses the symbolic symmetric matrix program, which has to be in the system and it has to be compiled for the Lyapunov to be able to work, right? So this is a problem that we have to solve, especially if all of the functions that I write are Cas functions, because I want them to work with symbolic expressions instead of just numeric ones. Which gives us the nice nice fact that we can like go here and inspect with all of these different we can do like tangent calculations and pretty much anything here. Like it's very nice to be able to use these stock graphing functions because they are so powerful. And that's why I did not decide to build my own apps to plot, like for example, the root locus or the Bodhi plot manually per se, especially the Bodhi plot, because I want to use like I want to do measurements on the Bodhi plot that I might not be able to do if it's generated just numerically instead of calculating the expressions for the gain and the phase. Right. Let's see here. We can look at other things. Let's just close it by looking at, for example, like the Nyquist plot or whatever. Just go to the Control S domain, go to the Nyquist plot, and plot it. Why not? It'll just give you half of the Nyquist plot here. If you want, you would do Shift plot setup and go on the negative frequency range, right? And then it'll give you the entire plot. It really doesn't need 200 steps for this. Let's just use a step of 1. So plot faster. Much faster, that's better. And then here you can see like exactly like how the diagram is drawn, and you can use it to assess stability and other things. And you know the direction that is being drawn from using like from translating through the T's here. Ooh, it's very fast. Let's go to the 0 first. Okay. So you know that this big curve here is going in the clockwise direction, and that other loop there is also going in a clockwise direction. So I find these things very useful. I find all of these little programs very useful for a control systems lecture. They just are not, like, they require some guidance to be used, and I would definitely have to write some documentation and improve them if I'd want to post them on the forum. And this is why I'm just sending this to you over DM, right? Because you're interested on it. So I guess that's it. And I hope you enjoy it. I hope you take a look at the code and write your own functions, because I can say that writing all of these programs has made me learn control systems much better than I did in like the class at university. Um, and that's it. Bye.